All right, moving on then. All right, so for laminar flow, the momentum boundary layer, the thermal boundary layer, those dictate three things that we usually care about as engineers. Like, we don't usually care about the boundary layer itself because, unless you're really sort of academic, you don't really care about it. What you really care about is the effects of those things. So the shear stress, right? The flux from the surface, the heat transfer coefficient. The boundary layer is dictated or dictates those things, right? The boundary layer dictates shear stress, flux, and heat transfer coefficient. Let's think a little bit about how that actually works. All right, so let's see. Let's start off by, come back here. So let's start off by coming up with kind of a conceptual model. So Q dot convection. So if I'm going to estimate the convection heat transfer from a surface into the free stream, what's a good approximate model for that, given, we're going to characterize this with resistances. So my approximate model for that is going to be, again, I have some, down here I have some surface at Ts, and I'm convecting out to the surroundings. So this is Ts minus T infinity divided by some resistance. So let's just write this out. And what is this resistance going to be? Well, what are we actually doing when we're convecting into the fluid? We see that there's this temperature profile, looks a lot like 1D conduction. We're actually conducting into the fluid, right? So this is our conduction for this conceptual model. All right, so our convection heat transfer is related to a conduction resistance in the fluid. Okay, what does that conduction actually look like? So Q dot convection is going to be Ts minus T infinity. Again, what is that resistance? Well, how far do I have to conduct? Right? If I'm conducting from the surface into the free stream, how far do I have to conduct? Delta T, right? That's the boundary layer thickness. So I have in the denominator delta T, and then I have the K times A, right? So that's my resistance there is 1 over that. So I'm conducting a distance delta T. K is, importantly, right? This is the fluid's conductivity, not the surface. Right? We're conducting through the fluid here. And then A is just the exposed surface, right? Okay, so then if I want to express this in terms of a flux, Q dot double prime convection, that means I divide by area and I'm just left with Ts minus T infinity. So times K divided by delta T. Okay, so if you think about this for just a second, we can actually notice something interesting here. Right? What do we normally call, or what's the rate equation we normally write for Q dot double prime convection? It's just H times the temperature difference, right? So what is that thing then? That's our approximate H, right? So this is approximately, let's write it a little more carefully. So this is our approximate version of H. It's just K divided by delta T. So all this time we've been assuming this convection coefficient is some sort of magically ordained thing that's just given to us and we have to use it. Well, no, it's actually a ratio of the conductivity of the fluid to the boundary layer thickness, right? And so for a lot of geometries, we just say, well, let's take some average boundary layer thickness. We'll call that H bar, right? That's our average heat transfer coefficient. If you want to pick it out at any specific location, you would just use the boundary layer thickness at that location, and that would give you your approximate H. Okay, so that's a really kind of useful conceptual model for that. Let's actually sketch out here what it looks like, though, as a function of position. So let me just draw some axes here. Sometimes it works. Okay, so if we draw, let's see, let's start with our thermal boundary layer. So the thermal boundary layer, this is coordinate X, this is 0 here. So if we draw the thermal boundary layer as a function of position, right at the leading edge, that thermal boundary layer is 0, right? It starts out at 0 and then it'll grow quickly. So that's going to look something like this. Right, and it grows according to what the square root of x. So it looks kind of like that. So we'll label this delta sub t. Let's draw the momentum boundary layer. Let's say this is for a Prandtl number less than 1. So it'd be like this. Delta sub m. Just to pick something. Okay, so let's sketch out what do we think the heat transfer coefficient H is going to look like. I'll draw this in green. So what is my H going to look like? If I plot H as a function of position, so what is H going to be at 0? Right? Infinity, right? So right at the leading edge, there's effectively an infinite heat transfer coefficient, meaning my surface temperature is exactly equal to my free stream temperature. Right? As I move away from that, then it's going to trail off, right? As the thickness grows. So it might look something like this, right? More or less. Doesn't quite get that flat, but you get the idea, right? So we start off infinitely high heat transfer coefficient. As you go out, it sort of trails off. So that's our H. And sometimes as we get into it more careful, I'll call this H at some position X, right? So it's a local heat transfer coefficient. Okay, so then what is our convection flux going to look like? So our convection flux is going to look also like it's starting off at infinite height, right? And then as you go on, our Ts minus T infinity is staying the same. So heat transfer coefficient is changing. So then it sort of follows along like that too. So this is Q dot double prime convection. Right, so you have these, this kind of behavior that you see. All right. Yeah, one thing to kind of point out. So if you were designing, let's say you were designing a heat exchanger and you wanted to have good heat transfer, what is something that you could physically do in designing that heat exchanger that would help you, right? What is something that you could do or that relates to the boundary layer thickness? Yes, exactly. Yeah, so let's say, yeah, you're moving along and all of a sudden you introduce a little, notches or something like that, and it disturbs the flow. Now, every time you hit this notch, you have to reestablish your boundary layer. And so now your boundary layer on average is much thinner than it would be if you just left it alone and let it grow. So that's a lot of times why you'll see in heat transfer enhancement, little microsurfaces that are causing the boundary layer to consistently break up and reform. Okay. Okay, so let's do kind of really quickly the same. I really need a separate slide for this, but same thing for shear stress. Shear stress. So we were talking about heat transfer for the most part in this class, but when we're talking about heat transfer, we also have to put it in context that we're moving fluid around, right? We have to keep in mind that there's viscous effects that we have to deal with. So this same type of model can apply here. So if we were to model shear stress tau s, what is our actual sort of analytical representation of that? It's mu partial of u with respect to y, evaluated at y equals 0, right? That's the definition of shear stress. So we're looking at how is that fluid shearing right at the wall, right? And that rate, that du dy, the rate of velocity change with respect to y dictates the shear stress. Okay, so if we want to come up with an approximate model for this, we could say tau s is approximately equal to mu, which is just a property, times, well, what's du in this problem? What's the biggest that du could be? We have 0 velocity at the wall, and we have u infinity out in the free stream. So the biggest velocity, the biggest du is u infinity. What's the dy in this problem? I think I heard boundary layer thickness. Yeah. So delta m. All right, so there's our little approximate model of what the shear stress would be. Again, this is assuming, right, if I draw this, it's kind of assuming I've got a linear profile here, which is not quite right? It's going to underestimate your shear stress, but as an approximate model, it's pretty good. Okay. One thing that you run into though, and why it's important to think about the shear stress is there's always, so let's say, so if I want a higher heat transfer coefficient, what's one thing I can do? Well, I can break up the boundary layer. If I break up the boundary layer, my delta is going to be smaller, momentum and thermal, right? But what happens to the shear stress if I have a very small delta? It's going to go up, right? So there's this constant like tug of war in heat exchanger design between low delta P pressure drop across the heat exchanger and good heat transfer. You're always fighting this battle, no matter what you do, right? It's sort of a fundamental characteristic of the system. Okay, that was really the only point for this slide. Okay, any questions before we move on? I have a few minutes left. Yeah.
So on that last slide, not that we look at you had those two curves.
Yeah, so if you're yes, so I mean they're related to the conductivity of the fluid, but it's basically they're related to each other. The convection is the product of the constant temperatures and the heat transfer coefficient, right? So they're just scaled by the convection coefficient. Okay. All right, so non-dimensional heat transfer and shear stress. We've now talked about shear stress having this, tau as the dimensional property, heat transfer coefficient as a dimensional property. Usually, though, when we want to talk about these types of coefficients, we want to do so in a non-dimensional way so that we can generalize it for any problem that we have, right? So let's come up with some really quick models for those. So we're going to start with, again, you've probably seen this, the Nusselt number. Okay, so the Nusselt number is a non-dimensional heat transfer coefficient. It is defined as, we'll call it nu, not nu like the Greek character, but nu, the first two letters, are now H times L characteristic divided by K. Right, that's our definition of the Nusselt number. It's a non-dimensional number. Okay, and if we want to actually kind of see how this looks in our approximate model, well, our H was just K divided by delta T. L characteristic is at least for external flow over a flat plate is X. Okay, and then we divided the whole thing by K, and then so that's going to say our Nusselt number is approximately just X over delta T. All right, that's approximately. So L characteristics over K, that is the definition. This is our approximate representation here. One thing to notice about this is the Nusselt number is really just a length ratio. Right? You kind of look at that, you can see it. It's a length X, that's how far we've gone over the plate, divided by the thermal boundary layer thickness. So for a really long plate, let's say, relative to a really thin boundary layer, you're going to expect to see Nusselt numbers that are pretty large, right? So it's just saying, how far have I had to travel versus how far do I have to conduct energy? It's kind of just this length ratio. Let's see, the friction coefficient. Friction coefficient is kind of the other side of this problem. So just one definition. So if we write tau, our shear stress, the actual definition of that is 1/2 rho U infinity squared times this CF friction coefficient. So what I mean, so we have shear stress that can be represented as the product of the momentum of the fluid, right? 1/2 rho U infinity squared times some coefficient, right? So if all of the momentum in the fluid that's moving goes into shear, it's sort of lost to the shear part of the force balance there, then CF is going to be 1. But normally that's not the case. There's some other things that are happening, heat dissipation due to shear. Not all of it goes to momentum. So you have this CF that's introduced. So we can rewrite this. So we're going to use tau is approximately equal to mu times U infinity divided by delta M. And so using this, that definition of tau, and then what we just wrote out, we're going to say mu U infinity over delta M is equal to 1/2 rho U infinity squared times CF. So let's rewrite this, solve for CF. That gives us 2 mu over rho u infinity delta m. Okay, continuing to rewrite, that's actually 2 times mu divided by rho u infinity times the square root of Reynolds number divided by 2x, okay? So that's one step. One more step here is going to be, you still have square root of Reynolds number here, but if you look at what we have this over here, this 2 goes away, where we have rho infinity times x divided by mu. Rho, what did I write here? Rho infinity, rho times u infinity, right? Times x divided by mu. That's the Reynolds number again, or 1 over the Reynolds number, right? So that actually is saying the coefficient of friction, at least according to our approximate model, is 1 divided by the square root of the Reynolds number. Okay, so using our conceptual definition of tau, we can say that the coefficient of friction is going to be related to flow that way. Okay, one last thought here before we wrap up is what's the exact solution? CF. So CF, I should make this up here approximate. CF is exactly equal to 0. So you guys would probably tell me this, 0.664 divided by the square root of Reynolds number, right? Does that look familiar from fluids? Laminar flow over external plate. And so that's our exact solution. So we're pretty close in terms of our definition, just off by a little scaling factor. Okay. Any questions before we wrap up? Okay. Lecture quiz today by midnight, 11:59, and I'll see you on Wednesday.